Portland has been in the news a lot lately, be it for the unwelcome involvement of federal law enforcement, or as the new home of the nation's most restrictive facial recognition ban. But today I want to take you back in time to 2017, to another instance when Portland laid at the intersection of technology and policing. The National Institute of Justice had just announced the winners of $1.2 million in prizes for its crime forecasting challenge. The challenge asked data scientists to develop algorithms to better predict the occurrence of crimes based on location. Thankfully, Team Anderton, named for the Precrime division head in Philip K. Dick's Minority Report, collected none of that prize money. I say thankfully because I was Team Anderton. Team Anderton was a canary in the data mine, dashed off over 2 weekends. Its forecast embodied my greatest fears for predictive policing. If it had fared well, it meant trouble. Luckily, it did not, but it still has something to teach us. What follows is the story of Team Anderton, a companion to the classic How to Lie with Statistics, updated for the digital age. Fed by inexpensive computing, statistics has a new name, data science. And although it can be used for good, there is a dark side. And as attorneys, we must be mindful that such misuse threatens the rights we have sworn to protect. The competition asked interest to make place-based predictions for crimes occurring in Portland, Oregon, over the 3-month period beginning March 1, 2017. These predictions were to cover different criminal offense types, for example, burglary, motor vehicle theft, over a variety of time frames, 1 week, 2 weeks, 2 months, 3 months. You can think of these forecasts as weather maps, except instead of predicting rain, they aim to predict criminal activity. Specifically, they ask participants to divide a map of Portland into a collection of cells and predict whether or not each cell was or was not a hotspot. It is an area in which one is likely to find calls for police service. These predictions were to be collected, and over the ensuing months, NIJ would compare them with the reality on the ground as it unfolded. To inform predictions, the Portland Police Bureau provided 5 years of records containing individual calls for service, their type, so burglary, motor vehicle, location, and date of the call. I learned of the challenge from this sponsored tweet put out by the MIT Tech Review. It reads, "Into the National Institute for Justice's Real-Time Crime Forecasting Challenge." Now, as you have, I had read Kathy O'Neill's chapter on the dangers of predictive policing. And though I really wanted to write something explaining all the dangers such a well-intentioned competition was likely to face, I wasn't sure what more I could add to the growing chorus of concern surrounding algorithmic bias. Actually, little did I know, I'd only have to wait a few years for the MIT Tech Review to join the chorus. Here's a more recent tweet, and this one's not sponsored. It's one of their articles, "Predictive policing algorithms are racist. They must be dismantled." There's actually a link down below in the reading. Anyhow, when I saw that first tweet, that's when I hit upon the canary idea. It's one thing to talk about how algorithms go bad, but to show the banal birth of such an algorithm seemed like a story worth telling. Now, the challenge rules spelled out its goals like this. The Real-Time Crime Forecasting Challenge seeks to harness the advances in data science to address the challenges of crime and justice. It encourages data scientists across all scientific disciplines to foster innovation in forecasting methods. The goal is to develop algorithms that advance place-based crime forecasting through the use of data from one police jurisdiction. I framed this tale as one of data science and algorithms gone bad. However, the missteps I describe are not exclusive to data science. In fairness, the term data science is still a bit contentious, meaning different things to different people, so some clarification is warranted. Here we will be looking at data science broadly as it relates to the construction of models aimed at describing, classifying, and predicting events in the world. We will apply the most general meaning of the term algorithm, a set of instructions one must follow to transform a set of inputs into a set of statements about the world as seen by our models. What makes data science, however, is the means by which it constructs these models. Customarily, this means looking for patterns in some subset of historical data, building a model based on these patterns, what we call training, and then testing, what we call validating this model against the remaining data. In later videos, we will talk about how this relates to the field of machine learning, but moving on. In practical terms, the final product is an algorithm that answers a question based on a set of inputs and its historic training data. So when a risk assessment tool says it's providing a statement about someone's likelihood to reoffend based on a few simple questions, there's actually a whole set of assumptions baked in. Those assumptions are an outgrowth of whatever data it was trained on. Spoiler alert, this is where bias often slips in. Now, once I read a press report on a legal tech startup that claimed it could predict the outcomes of legal matters with 71% accuracy. Upon reading this, I chuckled to myself because accuracy is probably the wrong metric for success. Why the concern? Because the distribution of winners and losers is probably unbalanced. Consider Supreme Court cases. A set of legal scholars polled for their predictions on SCOTUS outcomes came in with an accuracy of 59%. But it is well known that in the modern court, most cases are reversed. About 63% of cases are decided in favor of the petitioner. So a simple algorithm that always predicts the petitioner wins would be accurate 63% of the time. This beats our legal scholars. You can be accurate without being insightful. Now, medicine has known this for quite some time. If 1 in 20 people have a disease and you have a test for this disease that always comes back negative, it will be 95% accurate and 100% worthless. So when discussing the efficacy of such tests, medical professionals tend to speak of sensitivity and specificity, measures that focus on the number of true positives and true negatives, the logical siblings of false positives and false negatives. Data scientists often use a similar pairing, precision and recall. Precision is the ratio of true positives to the sum of true positives and false positives. And recall is the ratio of true positives to the sum of true positives and false negatives. The takeaway? You can be right for the wrong reasons, and accuracy isn't always accurate enough. In fact, there is a whole constellation of measures used to assess the quality of prediction / classification. The trick is choosing the right subset for the case at hand. Whatever the success metric, accuracy, some combination of sensitivity and specificity, or something entirely different, it's necessary to have some measure of what's true. If we are going to measure if an algorithm is making the right call, we need to know what the right call is. Sometimes that's easy, but most of the time in the justice system, it isn't. After all, that's why we have the justice system, to figure out what the right call is. That right call is something data scientists call ground truth. This is why I get anxious when people talk about replacing juries with algorithms. Often we're just making a guess or assuming that one thing can stand in for the other. For the policing competition, consider this simple fact. The data available for training and validation, the data against which the winners were judged, is not actually a measure of crime. It is a measure of calls for service. If there are crimes that don't result in calls, they might as well not exist. Consequently, the forecasts do not offer some insight into previously unseen criminal activity. It's not truly ground truth. They answer the question, where will we find crime, with where we always have. Perhaps you could account for potential sources of bias like over-policing by controlling for things like the frequency of police visits and neighborhood demographics. But if such a genuinely thoughtful model resulted in a map that differed from the traditional distribution of crimes, it wouldn't score very well. This is just because we aren't judging models based on some omniscient understanding of where crimes actually occur. Instead, we have to judge them based on our available data. For challenge participants, constructing and fine-tuning their models, this meant historical call data. Where will we find crime? Where we always have. Now, it doesn't matter if you're using fancy machine learning or a gut feeling. If you're evaluating the efficacy of a model, you're limited by your access to ground truth. If your finder of fact has to make guesses about what the right call is, you will always be saddled with their biases. What counts as true and how you measure success is a matter of the utmost importance. So what did the challenge use as a success metric? Actually, the challenge made use of two metrics. One, something they called Prediction Accuracy Index, PAI, and another measure they called the Predictive Efficiency Index, PEI. Prizes were awarded for both predictions, one with the highest PAI and one with the highest PEI for each categories. And you can find the definitions of those below in the rules. It's worth noting that only through the evaluation of PAI and PEI can one tack down the definition of a hotspot. That is, hotspots are those cells that perform well as hotspots under either PAI or PEI. Consequently, these success metrics impose a selective pressure on the models when produced. So it's important to remember that these different metrics embody different priorities. PAI is a ratio of ratios. The numerator, top part of the fraction, is the number of crimes that occurred in your hotspot divided by the total number of crimes in the study area, Portland. And the denominator, bottom part of the fraction, is a number of your hotspot's total area divided by the total study area. The best PAI scores occur when the numerator is big, so close to 1, and the denominator is small, close to 0. To score well, you're trying to capture as many crimes as possible with your hotspot while using the least area. The competition, however, placed a lower limit on how small you can make a cell, requiring that be at least 62,500 square feet. Consequently, it's easy to imagine a scenario in which one achieves a high score by focusing exclusively on high-density, high-value hotspots, to the exclusion of those predicting a lower density of crimes. That is, it's possible for the boost a hotspot provides to be more than canceled out by the cost imposed by its area, encouraging such a model to ignore some crimes, especially those that aren't densely clustered. For a cell to be classified as a hotspot, the model has to be really hot. Now, PEI, however, has a different set of priorities. It is defined as the number of crimes that occurred in your hotspots divided by the maximum number of crimes you could have gotten for an area equal in size to that of your hotspots. Consequently, the lowest density hotspots, those containing 0 crimes, can come at no cost. If you called every cell in your model a hotspot, you can get a perfect PEI score because the number of crimes that occurred in your hotspots divided by the maximum number of crimes would logically have to be equal to 1. That is the highest possible score. Unlike PAI, the focus isn't on finding the hottest spots, but rather on making sure that you catch every last call. Now, the competition mediated the greatest successes of PAI and PEI by requiring that the total predicted area of hotspots fall between 0.25 and 0.75 square miles. So there shouldn't be a PAI winner with a single 62,500 square foot hotspot, nor should there be a PEI winner with a single hotspot encompassing all of Portland. The tension between PAI and PEI is analogous to something called the precision recall trade-off. As a rule, models that optimize for recall are inherently optimistic about their abilities to correctly make predictions. This implies a higher tolerance for false positives than a model that focuses on precision. This is a defensible choice, but it is also a statement about priorities. The same holds true for PAI and PEI. They measure different things and represent different understandings of what it means to be the best. And this cannot be overstated. There is no single measure we can use to determine the best algorithm. Even if we believe ourselves to have access to ground truth, there are always trade-offs. I tried to think of a model that would be both intuitive and intuitively deficient. For example, overly simplistic. I think it's safe to assume that when most people are presented with a crime prediction algorithm, they expect that model to take into account a number of features. For example, weather, maybe time of year, unemployment rates, foreclosure rates, etc., stuff like that. So I wanted my models to subvert those expectations while being good enough to actually have a chance. I wanted the mere thought that they could win to make people uncomfortable. I wanted people to understand that in some way they violated a set of unspoken expectations. And so by so doing, draw those expectations into the discussion. I wanted to do this because all too often, these expectations are shrouded in a cloud of mathematics and left unexamined. Sometimes they're even locked behind legal black boxes marked proprietary. So I decided to take the following literally. Where will we find crime? Where we have before. Now, imagine a map of Portland, divided into a bunch of cells with the smallest possible area allowed by the rules, 62,500 square feet. These cells make up squares, except where they cross the borders or on the edges. Now go through all the historic data and place a tile of the same ties atop each cell for every call for service it received. In this way, you can imagine building a landscape of crimes or calls. This landscape will include numerous hills and mountains, with the highest peak atop the cells or the cell with the most calls. You can make different maps by looking over different time ranges or by including different crime types. Once you have these, the only question becomes how best to decide what to call a hotspot. It seems sensible that a hotspot should have more tiles or calls than non-hotspots. So I could call the highest peak a hotspot, leaving everything else alone. I could call every cell with at least one tile a hotspot, or I could split the difference somewhere in the middle. The question is where do I draw this line? What is the cutoff point that I should call a hotspot? Here's where the success metrics come into play. All I had to do was try every conceivable cutoff point from the least to most inclusive and pick the best, right? To be clear, all of the entrants are likely to have gone through a similar optimization process in that they will have somehow worked to maximize their performance along the success metrics. My method is just absurdly crude. Now, here are PAI and PEI for 5 different methods, landscapes. Each model excluded a common chunk of dates and draws from a different set of historical data. For example, the prior 2 weeks, the prior 6 months, etc. To determine what to call a hotspot, I simply looked at the X number of cells with the most tiles less calls. So a model with 200 hotspots is comprised of the top 200 cells by tile call count. The PAI and PEI you see are the scores for those models when used to predict the calls found in the common chunk of dates, those from which I did not draw tiles. You probably noticed that the PAI is highest for a low number of hotspots, while the PEI is highest for a large number. Those patterns weren't replicated in all of my models, but they were a general trend in most of them, especially those involving large call volumes. Given an understanding of PAI and PEI, this isn't surprising. Some of the literature cited by the challenge actually included a model with a PAI score of 6.59 for street crime. So it seemed unlikely that my model could compete on PAI given its performance. PEI, however, seems to be a novel metric, and I couldn't find a good benchmark against which I could measure my performance. Interestingly, as discussed above, it's actually possible to get a perfect PEI score of 1, and I started to find my model maxing out at 1 in a few of my test runs, when the total number of calls was very small. Remember, PEI wants to be sure that you capture all of the calls, and if you cast a wide enough net, you increase your odds of catching more of the calls. This behavior is probably what's behind the fact that there were ties for PEI in the final awards. Since the performance of PAI and PEI were at odds with each other in regard to where I drew the hotspot cutoff, it was necessary for me to choose a metric to maximize. I could have split difference, but there was no prize for models that balanced the 2 scores, a fact that I actually found a bit surprising. Winning meant having the highest PAI or the highest PEI. Consequently, I decided to optimize my model for PEI. I mean, after all, I knew I wasn't a contender under PAI. I found that a training period of 1 year seemed to work pretty well. So basically, I built a landscape based on the last year of calls for each category of crime and labeled the top 300 some odd cells in my grid as hotspots. I entered the same model for each time frame, 1 week, 2 weeks, 1 month, 2 months, and 3 months. That is, I only made new models for each of the offense types, not the time frames. Like I said, I wanted to keep it simple. If you want to see how simple, you can actually find the code I used to generate my entry linked below. Hopefully a few things are clear by this point. Chiefly, my models were dead simple. Clearly, the utility of such models must come into question. They are demonstrably doubling down on the status quo. There is no new insight here. Perhaps as a matter of triage, they could be useful, but such a use assumes we're happy with the underlying success metrics. And I strongly suspect this use case is not the one most often sought by consumers of crime prediction. I assume they expect prediction to involve more than a mapping of past crimes. I'm sure there are models capable of providing genuine insight. For example, I wouldn't be surprised if some of the models noticed that certain property crime types were clustered. Plausibly, this could be explained by an offender's geographic reach. And such an insight might be useful in tracking down a serial car thief. My concern mostly revolves around how these models are received and applied. To be clear, I commend the NIJ for conducting the challenge. However, I worry about the public's expectations and what has become of these algorithms that the competition helped birth. At the time of the competition, I worried consumers, meaning communities, wouldn't stop to consider the choice of success metrics, let alone question the defaults and the priorities they express. As we found, accuracy isn't always the right metric, and there are real costs associated with false positives. What happens to the relationship between law enforcement and a community when officers use science to justify over-policing? Incentives matter, even when they come in from an algorithm's conception of success. Since the competition, however, I've seen reasons to be optimistic. Santa Cruz has actually banned predictive policing, and LA, an early adopter of predictive policing, is stepping away. But I've also found reasons to be pessimistic. Just check out the article below from the Tampa Bay Times. Oh man, yeah. Anyhow, Anderson's dead simple models are easy to understand. Consequently, they're easily understandable as utter crap. Yes, they make predictions. They may even be good predictions under some metrics. But are they really the predictions we're looking for? As any student of mathematics understands, it's important that you show your work. We need to see more than the output of an algorithm before we can pass judgment on how well it's doing its job. So, is there room for hope? Well, a few weeks after the submissions closed, I caught wind of a startup hoping to provide predictive policing to law enforcement. And what made them different? Well, first, they wanted to adjust for or flag the biases in their data. Second, they were making their algorithms public so anyone could critique them. Heck, they had their code up on GitHub. Unfortunately, both their GitHub repo and their website have been shuttered since. Let's assume, however, that we're inclined to be optimistic. Maybe we can account for over-policing and its effect on producing training data. What happens, however, when bias-adjusted models suggest more invasive policing in the suburbs? An observation from Michelle Alexander's The New Jim Crow provides some food for thought. From the onset, the drug war could have been waged primarily in overwhelmingly white suburbs or on college campuses. SWAT teams could have rappelled from helicopters in gated suburban communities and raided the homes of high school lacrosse players known for hosting coke and ecstasy parties after their games. Suburban homemakers could have been placed under surveillance and subjected to undercover operations designed to catch them violating laws regulating the use of and sale of prescription uppers. All of this could have happened as a matter of routine in white communities, but it did not. Instead, when police go looking for drugs, they go looking in the hood. I love that paragraph, but too often this is where a talk like this might end, asking you to imagine a world where we treat the privileged in the way society has traditionally treated the marginalized. I understand this impulse, but it does clearly act as a wake-up call for those in power, but it frames the discussion around retributive justice. It's hard to remember sometimes that we are the nation that pioneered the penitentiary, literally a place for penitence. We used to believe in second chances. A more interesting question might be, what if we started to treat the marginalized the same way we treat the privileged? What if we recognized everyone's humanity? We've seen some moves in this direction in mainstream criminal justice reform around nonviolent drug offenses. But as John Pfaff makes clear, linked below, mass incarceration is not just a drug problem. We must examine how we respond to violent crime as well. And that's a difficult conversation. Perhaps Portland, however, does offer a lesson in hope. And as I record this, Portland has seen more than 100 days of protests in support of racial justice and police accountability. And this summer, millions of Americans joined in these protests. So maybe there is room for hope. The tale of Anderton, however, isn't just a warning about predictive policing. It's a warning about what happens when a lack of attention or fear of complexity causes us to measure the wrong thing. In a world of algorithms where measurement is king, we have to insist, as Chief Justice Earl Warren did, on asking a single question over and over. Is it fair? To do this, we must decide what we mean by fair, and we need to see the work that went into the prediction in order to check that. Metrics matter, and accountability can't take place in the dark. Algorithms can only optimize for values they can measure. If we fail to define fair metrics, we will fail to create fair algorithms. As the role of algorithms grow, it is incumbent upon attorneys to echo Warren's words. insisting on an answer to the simple question, is it fair? Now, engage with the materials below, and we can learn together how to help make that world a reality.